Hi, everybody. All right.
Hello.
So- okay. All right. So, anybody questions? Anything they want to discuss? Okay. If not, then let's get started. So there are a few things I want to cover today. I'm not sure if I'll take up actually the whole class time. We'll see. And I posted an announcement on Canvas that I'm going to give you guys a break from homework next week. I should have thought ahead and done that this week, um, maybe it'll be more fun to have it next week when it's like a less stressful week for everybody. So suffer through the end of this week and then get a break next week from doing homework. Um, okay, so we're discussing the space L1 of integrable functions, and I want to finish up some of the material in chapter 2 of the book today, and then I want to start chapter 3 next time. Um, so let's do that. So the first thing, oops, I should share the screen. The first thing I want to discuss is density in L1 of RD of various classes of functions. So this is a definition. A family G of functions is dense in L1 of RD if for every F in L1 there exists and every epsilon bigger than 0 there exists a G in the family G such that the distance between F and G in L1, so it's metric space density of RD is less than epsilon. So the distance between F and G is within epsilon. So this is what it means for a family of functions to be dense. And the theorem that we'll prove is that the following families are dense. So just to comment that this definition is the notion of being dense in a metric space. So a family G of, you could replace functions with elements of a metric space is dense in said metric space. If the following holds with where you're just replacing the L1 metric with some other metric. So this definition is specific for L1, but it's just a general, the same definition you can generalize to any metric space. So the following families are dense. One, the simple functions. Two, the step functions. And three, perhaps most usefully, the continuous functions. With compact support. So just some note. The support of f is, we say f has a function f is compactly supported if there exists a compact set K such that the support of f is in K. So, for example, if the in RD, what this amounts to is that the support of a function is contained in a large enough closed ball of radius n. If since compact sets are closely bounded, right? In RD, if there exists and such that, or R, maybe let's call this. The ball of radius R centered at 0, say the closure. This. So such functions are dense. So notation, so we'll call C0 0. RD is equal to all F RD to R or C such that F is continuous and compactly supported. So this is a useful function class to have. So this 0 on the bottom refers to compactly support, the compact support. And the 0 up top is continuous. And similar notation, so CK0 is functions that are kth with k continuous derivatives that are compactly supported. C infinity sub 0 is the smooth functions with compact support, etc. Okay, so let's prove the theorem. So we're gonna prove it in steps. So the proof. First, let's try and prove that the simple functions are dense. So this is just going to be a consequence of the dominated convergence theorem, or essentially a corollary of it. So let f be an L1 of RD, and just without loss of generality, assume f is real valued. Not negative, because otherwise we'll just study the positive and negative parts of f separately. Not negative. So with under these two assumptions, in general, study positive and negative parts separately. And then just the key step is that we've already proved that we can approximate f from below by simple functions, right? We know there exists a sequence phi k that increases to f pointwise. And then therefore, the phi k's are simple. Right, we proved this fact a while back, and then by dominated convergence, theorem, we can interchange limit and integral. Obtain this, right? Because since we have pointwise convergence of the functions, and they're all the phi k's are bounded above by an integrable function f. F plays the role of the dominating function in the dominated convergence theorem. So then we're done. 2. So now, uh, since we've already proved that the simple functions are dense, if we want to prove step functions are dense, we just need to show that next to any simple function, we can find a close enough step function in L1, right? So it suffices, this is by triangle inequality, to approximate simple functions by step functions. So this is, it suffices to do this. And in fact, so without loss of generality, we could take f to be a simple function, but then we can just ignore, we could just do the argument for each of the components of a simple function. In fact, we can just take f to be the indicator function of a set, right?
I have a quick question for you.
Yeah.
So when we say like approximate simple functions by step functions, so part two is to look at step functions, right? So
Yeah.
we're
So
approximating step functions by simple functions, or?
No, we're going to try and show that step functions are dense. And so since we already proved that the simple functions are dense, we could just say that f is a simple function and try to find a step function close by it. So we want to approximate, we're going to approximate simple functions by, we're going to show that we can find step functions are arbitrarily close to any simple function.
Okay.
And then by part one, since we know, so start with a general function, first approximate it by a simple function, like get within epsilon over 2 of it with a simple function, and then approximate, then we're going to show that we can get within epsilon over 2 of that simple function by a step function.
Okay.
And so therefore the step function is with an epsilon of f, since it's when since right,
use a triangle inequality. Okay, right. Got it.
Yeah. So in fact, we don't even need to take f to be a complicated looking a complicated simple function. We can just take it to be the indicator function of a measurable set, right? Immeasurable. And then now we are gonna use our knowledge of the structure of measurable sets. So we know, so again, we've done all the hard work already. We know there exists almost disjoint rectangles Rj such that the measure of the symmetric difference, E symmetric difference, union from J equals 1 to M. So there are finitely many of these, in fact, is less than or equal to less than or equal to epsilon. And therefore, chi E, and we can call this psi, which is the sum of chi Rj, of the indicator functions on Rj, J equals 1 to M, differ on a set of measure less than epsilon. Therefore, chi E minus psi in L1 is less than or equal to epsilon. Maybe I need a factor of 2 here or something. Okay, so that's it. It's just this is just one of Littlewood's principles, right, about measurable sets, or almost disjoint union of rectangles. And then finally, for 3, it suffices to assume that we're to approximate indicator functions on one rectangle, right? Since we know that step functions are dense. So finally, it suffices by part 2 to assume that f is just chi r, where r is equal to a rectangle. And in this case, so let me just draw the picture how to do this. R is in dimension 1. R is just an interval from A to B. Chi R is an indicator function on this interval, on this integral. And I want to find a continuous function that's compactly supported that approximates this. So which continuous function do I pick? Well, let me just make one like this. This theorem, at least, is not rocket science. This is, let's say, A minus epsilon and B plus epsilon. And this is now G of X. So then G is continuous with compact support. I just make it 0 everywhere else. And then therefore, F minus G in L1 is less than or equal to 2 epsilon, right? Because this is height 1, and I have a triangle. Yeah. I guess it's actually epsilon, right? It's less than epsilon. Because I just get the mass. I'm just off by the mass here of F and of G rather than the mass here of G. And this is 1/2 the base times the height. Height is 1, base is epsilon. So this costs me epsilon over 2. This costs me epsilon over 2. So I get epsilon. And then for dimension D, so the general case, R is just going to be a rectangle, right? Is just a bunch of intervals, right? And you just do this same construction for each interval, the continuous function. Okay. So one more bit of notation. So that finishes the proof of the theorem. Are there any more questions about the theorem or the proof?
There are two, if you don't mind.
Yeah, of course.
Because I remember established that any measurable function can be approximated almost everywhere by step function. So
yes,
can we directly apply that to proof two?
Sure.
Proof two.
Yeah, sure. Yeah, that should work too, right? We proved that. So we took a measurable function and approximate it almost everywhere. Say a non-negative measurable function. Say we can approximate it by step function. Yeah, by step functions. We can find a sequence of step functions that converges almost everywhere to it, right? So, so that should suffice to apply dominant convergence, just like in step 1.
Mm-hmm.
And if you recall how we proved that, we use the same fact about measure.
Yeah.
So the proof that is gave here is the same proof that we use to prove that theorem about approximating almost everywhere too, just by just using this fact.
Yes.
Yeah.
Yes.
Right. So yeah, but yeah, we could. I think you're right. We could directly apply that.
Mm-hmm. And also a second thing, as you draw the figure on how we approximate the indicator function of rectangle, I just think if we replace the straight line by some kind of bump function, can we actually prove that C infinity
Yep.
stands in L1?
Yep. So this is all I did here. Um, so all I did here was shoot for a continuous function. But then, like you say, like, oh well, I seem to needlessly put this corner here, in this corner here. I could do it smoothly. I could do it in a C1 fashion, and then you say, well, if I do it in a C1 fashion, why don't I do it in a a C2 function, in a C2 fashion, etc. So you can do this for any. You could just smooth out these two corners to do CK for any K, and then to get C infinity, like you say, we need the existence of of a of a smooth, infinitely differentiable bump function to do this, which there exists such a function. You could just build off the exponential functions. So what you do is just have this die off. You use some type of exponential function to make it die off here like this, and then same here. So yeah, you could just generalize this argument a little bit to work a little bit harder uh, to prove that C infinity with compact support are dense in L1, and that's a useful fact because it's often it's nice to work with nice smooth things, even more so than to work with continuous things. But yes, let me stop with writing. So let me just give that argument as I did in words, rather than do formulas, because I write down formulas. Right. So that's maybe a good exercise to do on your own. So maybe I'll just give it as an exercise. But you're exactly right. We could just work a little bit harder. C infinity 0 is dense in L1. So for many purposes, you can work with infinitely differentiable compactly supported functions, and this is how a lot of arguments go in analysis, where you try to prove something. You want to prove something about some class of functions or something like this, and you try to do it first for continuous functions or smooth functions with compact support. Maybe you need to integrate by parts, or do various things like this, various manipulations, which you can justify for such functions, but can't necessarily justify for the thing you're interested in. And then after the fact, try to use a density argument to conclude for the general class of functions. So that's a very standard type of argument in analysis, and so it's very useful to have nice smooth functions to approximate with. Yeah, but I'll leave this as an exercise. Like as you say, this amounts to existence of a bump function, what's called a bump function. A bump function is just a compactly supported C infinity function. Okay, so any other questions? The takeaway should be that L1 is a nice space. That's nice space of functions. C infinity functions with complex support are dense in it. Okay, let me make this. Let me just introduce this last bit of notation, or not last bit of notation, but another bit of notation for a measurable set E. RD can define L1 of E to as follows. So F on E set F twiddle to be equal to F on E and 0 on RD minus E. And then the L1 norm of F on E is just given by the integral of L1 of the L1 norm of f twiddle on RD. So in this way, you could define the space of integrable functions on a measurable set E. So D equals 1. Say you're only integrating from 0 to infinity, for example. Okay, so a few invariance properties of the integral. Invariances. So, and these are all going to arise from the invariances we discussed for measure, for measurability, for the Lake measure. So if I have f from RD to C, say, I can define the translation of f. So f sub h of x is just given by f of x minus h. So this is translation by h. By h, and then one invariance property is translation invariance of the integral. So if f is in L1, this implies that the translation of f by h is in L1 for every h. Sorry, for every h in RD. And star, and moreover, and star, the integral over RD of f of x minus h dx is equal to the integral over RD of f of x dx. So the integral is in fact invariant under translation. So let's prove this. Save the file. Well, on the one hand, if f is equal to indicator function on a measurable set, fh is equal to the indicator function on the translate of that set, where eh is defined to be the set of x x minus h, x plus h, or x minus h. Like this, and then the measure, we know we've already talked about the measure of EH is equal to the measure of E. So therefore, star holds for all simple functions. Functions, and then the story is now familiar. If f is a non-negative function, let phi n, maybe I should call this phi k. I don't know which looks more similar, like phi k, simple functions, such that the phi k's increase to f as k goes to infinity. We'll just need this fact almost everywhere, in fact. And that implies that phi h, actually, let's the translate of the phi k function should increase to fh, and then star follows from monotone convergence theorem. Okay. And then lastly, for general, we have integral of f of x minus h. So we just look at the function absolute f. This is equal to integral absolute f, which now implies that this is an L1 of Rd, and the L1 norms are the same. The L1 norms are, after all, just a matter of the absolute value. Okay. 2. Dilations and reflections. So delta to the d integral of f of delta x dx is equal to integral of f of x dx. So if you rescale f, it amounts to a factor of delta to the d. And so this is useful to know. And if I perform a reflection, then I don't change the integral. Again, these are integrals over all of Rd. So, and again, these will follow from the analogous properties. So you prove it for a simple function, or rather just for the indicator function on a set, using the same invariance property of the measure of the set, and then approximate a non-negative function by a sequence of simple functions, etc. For a general linear transformation, if you apply a linear transformation to x of delta or a linear transformation, what you get here would be the determinant of linear transformation. So you get this, rather than delta to d here, you get the determinant of whatever linear transformation is. Okay, the of interest, of much interest to us is convolution. Before we get back to Fourier analysis, if I take two functions f and g, both measurable functions. So I want to tell you when I can make sense of the convolution of two functions like this. If I have two functions like this, and the functions for fixed x, y gets mapped to f of x minus y, g of y is integrable. Then the function y gets mapped to f of y is also integrable. So if this function is integrable, then this other function is also integrable. And f convolve with g of x is equal to integral of f minus y. Y, the concept is this is equal to f of y. These two are equal to each other. So if one is integrable, then the other is integrable, and they're equal to each other. This should be this looks like a G. This should be a Y. Okay, so so therefore, convolution is a commutative product. So this is equal to commutative product. Some applications of these invariances. Just a quick remark. So dx over x the alpha, set x bigger than epsilon. Just this is now by dilation invariance. This is epsilon to the minus alpha plus d integral over the ball radius 1 dx over x the alpha. This is if alpha is bigger than d. And by, again, using the dilation invariance, if I integrate inside a ball of radius epsilon, dx over x the alpha, this is equal to epsilon minus alpha plus d integral. Integrating over the ball of radius 1 if alpha is less than d. These are helpful for computation, knowing some integrals like this. And dilation invariance. Okay, so now one other application is that is continuity in L1 norm. So translations and continuity. So recall that as h goes to 0, if and only if f is continuous at x equals 0. So this is a definition of a continuous function at a point x. At x. It's continuous at a point x. If its translation by h tends to f as I let h go to 0. But for measurable f, can be discontinuous at every x in Rd. Right, so measurable functions might have no points of continuity. However, you always have continuity in the L1 norm. However, if you're an integrable function. However, always in L1 norm. What do I mean by this? For the following proposition, if f is in L1 of Rd, then this is true. The L1 norm of the difference between f and its translation by h goes to 0 as h goes to 0. Sorry, this is frozen. It keeps freezing on me. Okay, so how do we prove this? So no matter how nasty of a function f is, in the pointwise sense, you always have continuity in norm. The proof, we're just going to use the density of continuous functions with compact support in L1. And it's basically just going to amount to that. So for every epsilon bigger than 0, find RD such that the difference between F and G and L1 is less than epsilon. And then now I'm just going to write F. So write F is equal to, sorry, I want to write F minus FH is equal to F minus G plus G minus GH plus GH minus minus FH. Okay, and just note that so the integral of GH minus FH is equal to the integral of F minus G, right? It's just a function translated by H, and both of these are epsilon size. So now it just amounts to showing that this integral can be made small. It goes to 0 as H goes to 0. So note, just by the noting translation invariance, FH minus GH is L1 less than 0 by translation invariance. And goes to 0 as H goes to 0 by dominant convergence theorem. Since G is continuous with compact support. So in particular, G is an integrable function. So you can use dominant convergence for this. Therefore, if H is less than delta and absolute value is small enough, G minus GH in L1 is less than epsilon. And therefore, less than 3 epsilon. If H is a norm less than delta. Okay, so we have continuity in L1. Any questions about this theorem or the proof?
I thought that was a little fast for me. Could you explain how you use the dominated convergence term?
Yeah. Okay. Okay, so now let's put this in a bubble. Use of DCT. Okay, so G is RD, and in particular, integral of G is finite. And now I want to look at, the claim is that GH tends to G as, or rather in L1, right? This is in L1. right. So this is what we're trying to show. So what is this? So let me. So what does this amount to? So this is so g h minus g and L1. This is equal to integral of absolute value of g of x minus h minus g of x dx and L1 rd. And I'd like to take the limit as h goes to 0, right? So so in particular, so let's look at any sequence. So let's let hn goes to 0 be a sequence. But it'll be any sequence, okay? So it suffices to show that this tends to 0 along any sequence of h's tending to 0, right? Minus hn. Okay, so this is my sequence of functions right here. And I know that the sequence is bounded above. So note G is less than or equal to, say, 2 times what's this? Some constant times g of x for every n. So how do I know this? Okay, how can I assume this uniform bound like this? Well, the point. Okay, so I need to use I'm gonna need to use I'm gonna need to use the maybe what should I say here?
Is it enough to say that?
Let's just do this. This is less than or equal to so G is continuous, implies that G of x is less than or equal to m. It's bounded.
Yeah,
right?
I was gonna say that.
Yeah, it's bounded as continuous. It's so it's bounded, so it's 2m. So we have a uniform bound, and now we know that for h small enough, as long as n is n is large enough or h is small enough, I've only the support of gh minus x g of x minus hn minus g of x is only like is contained in say twice the support of g, right? Like so I can find a big enough ball so that this remaining thing is still and there exists. So let me just write this, and there exists an r bigger than 0 such that support of gh minus g is for every, say, h smaller than 1, for example. So now the integrable function that I dominate this by is just the constant function 2m. But importantly on this ball, which is integrable because I only have to worry about a large ball of radius r, right? So so this and finally integral on the ball of radius r about 0 of 2m is less than or equal to a constant times r to the d times 2m. So I dominate these by a constant integrable function. The point is so just like this is a rule of thumb is once you have a fixed concept, then you're going to be good to do dominating conversion. You could use your dominating function just to be a constant function, right? Which is integrable on a fixed complex set. Does that make sense, Mike?
Yeah. It sort of seems like you're you could also use just the boundary convergence theorem. Is that true?
Yeah, right. Because we can find a fixed measure. We can just take our bounded set to be the ball of radius r, right? And then these are bounded functions there. Yeah.
Okay.
Yeah, exactly. Yeah, I guess once we're on a fixed compact set, then the dominated convergence theorem can just be replaced by the bounded convergence theorem, right? With a sequence of bounded functions, rather. Yeah. Okay, and so you see crucially how we use density of continuous functions with compact support though in this proof. Like none of this latter part of the proof, this use of dominated convergence, works sort of without for general f. We have no way to exchange integral limit kind of. Okay, yeah, thanks for the question. That was too fast. Too fast of me. Okay. All right. So the next thing I want to talk about, and which I'm going to avoid proving in class, is the Fubini-Tonelli theorem, which tells us it's an incredibly important theorem because it tells us the conditions under which we can switch the order of integrals or compute an integral over Rd as an iterated integral. So let's write Rd as a cross between Rd1 and Rd2, where d1 plus d2 equals d. And let's assume that these are integers with bigger than or equal to 1. If we let z be an Rd, we'll write z is equal to xy, where x is an Rd1, y is an Rd2. And if we have a function f from R, D to C, can write f equals f of x and y. F of z is equal to x of x, y. And we can consider the slices. So the slices of f. For y fixed, I can consider the slice fy of x is equal to f of xy. So I want to just fix y and then vary x. And for x fixed, I want to consider the x slice as a function of y, which is just again f of xy, but for x fixed. So a priori, it's not clear if, so a couple of comments, or maybe one more notation. So, and we could similarly slice the sets, consider slices of a set. So if I take E to be a measurable set, EY, E, a subset of RD, this Y slice of E is all X in RD1, such that X comma Y is in E. And EX is equal to all Y in RD2, such that X comma Y is an element of E. So I can take a set and consider its slices. Let me draw a picture. So here's a set. Here's Y. This is supposed to be RD2. This is RD1. I'm going to take X here. Then this is the set EX. So it's a set of all Y such that X, Y are in Y. And in blue, I'll draw the set EY. EY. And one comment, so a remark, is that even if E is measurable, it's not clear that these slices are measurable. So remark, warning, given F measurable, not clear that Fy is measurable. In fact, it's not even true for the sets. So even for simple functions, we could take E to be that funny non-measurable set that we constructed cross 0, which I think you may have done something like this in your homework. So this is not, say, non-measurable. The measure of E is 0 because it's a subset of RD, but E sub 0 is, the slice E0 is not measurable. Say this is an R2. Okay, so this is an example where the set itself is measurable, but but one of its slices is not measurable. Okay, however, we have the following theorem. So this is the theorem due to, this is Fubini's, called Fubini's theorem. Fubini's theorem. So if f xy is integrable, on RD, then for almost every y in RD, in RD2 rather. So it doesn't hold everywhere, but for almost every y in RD2, the slice f y is integrable. On RD1, 2 integral over RD1 is integrable on RD2. So this, note that this is a function of y, right? So for each y, I compute this integral in x and I get a function of y. This is, the claim is that this is integrable on RD2. And part 3, the integral of f on all of RD is equal to the iterated integral. Integral over RD2 of integral over RD1 f of x, y. So I integrate this slice dx, dy. So if I want to compute the full integral, I can just compute the iterated integrals. Okay, this is, you'll remember doing things like this in your calculus class, and the Fubini's theorem gives you the conditions in which you can do this with the Lebesgue integral. The assumption is that f is itself an integrable function. All right, so it might be hard to say that this f is integrable without being able to compute the iterated integrals. So in practice, what one does is one pairs Fubini's theorem with what's called Tonelli's theorem. And they're commonly just referred to all as just Fubini's theorem too. Here, so theorem, Tonelli's theorem, or the whole theorem is called Fubini-Tonelli. It's stated different ways, different places. I guess the whole thing is due to Fubini. Tonelli formulated this part, it seems. If f is non-negative, measurable on RD1 across RD2, so measurable function RD, then for almost every y in RD2, so importantly for almost every y, the function fy is measurable on RD2. This is, again, just emphasized for almost every y, right? Have I?
Should it be
RD1? Sorry, yeah. Is that what someone was going to say? RD1. Okay, good. Yeah, sorry. Sort of type up my notes. Integral over RD1 of fy x dx is measurable on RD2. 3, this is for almost every y, this is measurable. And third, integral of RD2 is equal to f of x y dx dy. So what you do in practice, these are paired together. Given f and the measurable functions in RD, we want to compute an integral of f, right? So this is often the problem you're faced with. You're given in a function f, a measurable function f. You'd like to compute you want to compute f, integral of f. So first, apply Tonelli to absolute f. Then, which tells you that you have measurability of the slices and the almost everywhere. Then freely compute the iterated integrals. Compute iterated integral. Of absolute f. So if you can compute the iterated integrals of absolute f, and this object is finite, then it's equal to, then in fact, right, then it's equal to this. So this is all with absolute f in here. Then the iterated integrals is equal to the integral of absolute f. That tells you that f is integrable, right? If these are finite, so you compute the iterated integrals in any order that you like. If they're finite in one order, if these are finite, then you can apply Fubini, which implies that f is integrable. Then compute integral of f using iterated integrals. So the moral of the story is you first put absolute values on f, compute the iterated integrals of the absolute of the function of the absolute value of the function. If that's finite, then that tells you that f is integrable. And then you can apply Fubini's theorem to the function without the absolute values on it in sort of regression, as you like. Compute either the iterated any iterated integral that you like. So that's how you do Fubini in practice. So the point is that first if you can put absolute values on f, and just compute any order of iterated interval that you like, but with absolute values on the whole function, then and everything stays finite. Then you're good, and then you can swap the integrals however you like. So that's the punchline. I'm not going to do the proof of Fubini to nullity theorem in class, and I encourage you to read that in the book. It's presented very cleanly in the book. And then there's also in the rest of that chapter, there's also some, there's some consequences of Fubini to nullity, like trying to decide, study the products of sets, products of measurable sets, and understand the measure of the product, measure of a product of sets. When is that equal to the product of the measure of the sets, etc. So there's some useful consequences of Fubini to nullity, and I encourage you to read the rest of the chapter. The proof is not super instructive, and it's a little bit long, so it's not something that's really helpful to watch me do in lecture, I think. It's one of those theorems where you should do the proof once and understand it once for yourself, convince yourself that it's true, never think about the proof again. And just remember what the theorem says. There are a bunch of those. Another example of those is existence of a bump function. So everyone should construct the bump function once for himself, and then from there on, you can forget how you did it, and just you have to live your life like this, kind of. So or else you never go forward. So some things you just do once, and then remember that you could do it. Of course, you have to do it right the first time. So yeah, it's important that you do it once and do it right. So speaking of politics, there's a mathematician. He was a former mathematician. It's kind of a tragic story. His math career was kind of tragic. In his thesis, he proved a very interesting, or his thesis contained a very interesting result. And he got a very fancy postdoc, very fancy position after this. Then he wrote a couple other papers. He wrote a sequence of papers, kind of all really relying on this, on some things in this first paper. So he was kind of like knocking down a bunch of important results in his field. His papers were appearing in all the best journals. It was like 3 or 4 papers. Co-authored a paper with some other senior mathematicians that appeared in a nice journal. And then a classmate of mine, when I was in graduate school, or he was 1 year ahead of me, started studying this guy's work, and was able to find a counterexample to the first theorem that this guy proved. So that he was relying on some lemma that was just completely false. So this is what I mean, is do it right the first way. So this whole guy's career, you can't write wrong. People write wrong papers, but it's hard to come back. It was a little bit hard. So this was devastating to this guy, because his kind of whole career was built on this false lemma that had a very clean counterexample. So where the politics come in, the guy, rather than continue, you still had a position. He could, try to just retract all of his previous work and start from scratch, maybe. But he decided not to do that, and instead he went into politics. And now, in fact, he's a rising star. It's not super hard to find out who this person is, I guess. But he's a rising star in the Democratic Party in Chicago. And he uses his, he's a former mathematician and everything. So this is part of his persona as a politician. But anyway, it was an unfortunate story where I told you can do things once and then forget the proof, but you just have to you have to make sure that the proof is correct if you're going to forget the proof. So anyway, yeah, don't. The moral of the story, I guess, is don't don't prove wrong theorems. So all right, I'll stop here. Let me see if there's questions in the chat. Oh, Andy. Thanks, Andy. That was fast. Yeah, my funny enough, my classmate who discovered the counterexample's name is Tom Church, and now he's shockingly left math too. So I'm not sure what's going on. There's something funny about that area, I guess. But Tom, I think, recently left math as well. So yeah, it was a surprising. It was a juicy story when I was in my early days at Chicago. And the classmate or a guy in my a year ahead of me, he was like it was like a legend as we were graduate students for finding this counterexample. Destroyed this guy's career, but still he wasn't trying to. He was just trying to understand the theorem. So anyway, yeah. So I'm not sure. Thank you, Tyler. Okay. Okay. All right. I think I've said enough. Yeah, this is not to say I mean I might be a very good politician and stand for good things. There's nothing to do. It's very easy to make mistakes. Everyone has mistakes in their papers. It never happens that you write a paper that doesn't have some mistake in somewhere, and it's a matter of whether the mistake is fixable or not. If there's a counterexample to the whole thing, then that might not be a fixable mistake, but it's really easy to we shouldn't dance on this guy's grave somehow. It's really easy to do this. It's really easy to make mistakes. What's hard about being a mathematician is that you are ultimately like responsible, like you are alone are responsible for finding them somehow before you try to publish something. And then anyway, I'll stop there and go. Sorry, is there a question?
Yeah. The results you obtained for L1 are they also valid for LP and L infinity?
Yes.
All these theorems, like you can approximate.
Yes. So we haven't defined LP yet, but we will soon. Maybe next class or the class after. I'm not sure what's happening with my notability, but the density theorems are and the continuity result are also valid for LP for any p bigger than 1. And L infinity, that case is this is somehow we studied this norm already a bit, but we'll get to this. We'll get to this a little bit later. God, I'm going to close the chat.
Sorry.
No, it's okay. It's okay. I just don't want to. I don't want to start. I don't want to confuse my laughter with laughter thing. The chat is. Feel free to share anything you guys like. But yeah. So everything that I said in class today holds for LP for p bigger than 1. P bigger than or equal to 1. And we'll discuss a bunch the other LP norms as we go on in class. They start becoming important. L2 will be important for Fourier analysis.
Yeah. Will we also see Sobolev spaces?
Sobolev spaces. Yes. It depends on how far we get. Maybe towards the end of the class, but we already started seeing the Sobolev spaces for when we were studying Fourier series. So we started seeing the Sobolev spaces for 2 pi periodic functions, and we'll see how far we get if we're discussing Sobolev spaces for functions on the line, for example, or an RD. But that we did talk about the Sobolev spaces without saying well, okay, we'll make it more precise when we come back to Fourier analysis, because before we were discussing Riemann integral functions and now that we have Lebesgue theory, we can go back and define and give proper definitions of the L2 based solvable spaces for functions on the circle.
Yeah. Thank you very much.
Okay. Please do not share the Daniel Biss story with any news organizations. As far as I understand, he's a reasonable politician. So I've kind of lost track of his career. I think he was at city. I think he was at city council level, or as an alderman maybe in Chicago. Aldermans are pretty powerful in Chicago. So he was rising quickly, but I'm not sure where he is now. I think it seemed like the plan was at some point he was going to run for Congress. But anyway. Okay. Well. Yes. The recording is on. Yeah, I haven't said anything that I regret yet. So, but thank you for reminding me the recording is on. All right, guys. Talk to you soon.
Thank you.
Sure.
Thank you.
Thank you.
Thanks, guys.
You still have an office hour today, right?
Yes, I have office hours.
Okay, cool. Just want to make sure.
Yeah. Okay. Bye, guys.